Hello viewers, welcome to this session on carboxylic acids. Our today's session is planned like this, that first we will review what we had done in our previous session. We discussed in our previous session about substituted acids. Amongst them one were hydroxy acids, and today we will discuss some specific examples of hydroxy acids. We will talk about their preparation and properties and some of their uses. The three hydroxy acids which we are going to discuss today are malic acid, tartaric acid and citric acid. And then finally, we will summarize our today's work. We discussed that hydroxy acids are those acids in which one or more hydrogen atom in the carbon chain are substituted by hydroxyl group, and they were classified as alpha hydroxy, beta hydroxy or gamma hydroxy etc., depending upon the position of hydroxyl group on this chain. I discussed that these hydroxy acids are very useful for us. They are used in medicines, cosmetics and in food items. But from our natural sources, that is basically from fruits, we get some common hydroxy acids which are having more than one carboxyl group and hydroxyl group with them. These are malic acid. Malic acid is a 4 carbon acid where 2 carbons are present as carboxyl group and 1 carbon contains hydroxyl group. Second is tartaric acid. It has got 2 hydroxyl groups and 2 carboxyl group. Then third is citric acid, which is a tricarboxylic acid. It has got 3 carboxylic acid group, 1, 2 and then third, and it has got 1 hydroxyl group. So, we will talk about their preparation, properties and uses today. First, let us take up malic acid. Malic acid has got 1 asymmetric carbon atom here. So, it is optically active and 2 optical isomers of malic acid they exist. Malic acid mainly occurs in sour apples, grapes and berry fruits. It is obtained also from apple juice or from berry fruit juice. Mainly berry fruit juice is used for this. This juice from the fruit is treated with lime, that is calcium hydroxide. In that case, the calcium malate is precipitated, which is insoluble. It is filtered and then it is treated with calculated amount of dilute sulfuric acid to give us malic acid. Chemically, it can be synthesized from some other compounds. One of them is by the hydration of malic or fumaric acid. We have discussed about these acids while discussing geometrical isomerism. This is the double bond present between these 2 carbon, and each of the carbon has got 1 hydrogen and 1 carboxyl group. The cis isomer of this acid is called malic acid and trans isomer is called fumaric acid. We take any of the isomer, when water is added to it in presence of acid, we get malic acid. Then we can get by the partial reduction of tartaric acid. Tartaric acid has got 2 hydroxyl group and one of it can be reduced with hydridic acid, we will get malic acid. Malic acid can also be obtained from bromosuccinic acid, and bromosuccinic acid itself be obtained by the Hell-Vollard-Zielinski reaction of succinic acid. This is alpha bromo with respect to this carboxyl. So, replacement of this bromine is easier, and even with mild base like moist silver hydroxide we get malic acid. Then its properties. Malic acid itself behaves as alpha hydroxy acid with respect to one carboxyl and beta hydroxy acid with respect to other carboxyl group. And one of the property which we discussed earlier while discussing the properties of carboxylic acid, hydroxy acids, that was action of heat. This malic acid, when it is heated, it loses a water molecule from here, because behaving as a beta hydroxy acid, it can easily lose a water molecule. And then the 2 carboxyl acid also, they eliminate a water molecule and we get malic anhydride, because these two acids can eliminate water molecule if they are on the same side. Means if after the loss of this water between these two carbons we get malic acid, then it will be converted into malic anhydride. But if when this water molecule is lost and we get fumaric acid, then it cannot be converted into any anhydride. So, malic acid on heating will give us a mixture of fumaric acid and malic anhydride. Malic acid can be reduced with HI, and on reduction with hydridic acid this hydroxyl group will be reduced and we will get succinic acid. It can be oxidized. On mild oxidation this secondary alcoholic group is oxidized into keto group, and this is called oxaloacetic acid. This carbonyl group can undergo a keto-enol tautomerism with this CH2. This is the keto form and it can exist in the enol form also. So, oxaloacetic acid exists in both the forms in equilibrium. Malic acid is used as food acidulant. Food acidulant means it is added to some jams, jellies, toffees, candies, etc. And it is used as a remedy for sore throat also. Next acid we take up is tartaric acid. This is the structure for tartaric acid, where 2 carboxyl groups and 2 hydroxyl groups are there. It occurs in grapes as potassium salt. The main source of tartaric acid is grapes only. Then another source is tamarind. The main source of tartaric acid, as I said, is grape juice. When grape juice is kept for some time, then some precipitate comes out of it which is called argol. Argol is actually potassium acid tartrate, means that tartaric acid where one carboxyl is there and one of the carboxyl is present as potassium salt, and this separates during the fermentation of grapes. When grape wine is prepared, it gets separated. This potassium acid tartrate is treated with calcium hydroxide, that is lime. Now, what happens? Some of the molecules of this, obviously half of it is, they get converted into the potassium salt and half of these molecules are converted into the calcium salt. Calcium salt is insoluble, it is precipitated out and filtered, whereas dipotassium tartrate, the dipotassium salt, is soluble in water. Now, to this aqueous extract further calcium chloride is added and this soluble potassium tartrate gets converted into insoluble calcium tartrate, which is also filtered. So, the solid precipitate from this and the first source, both of them are mixed and then they are treated with calculated amount of sulfuric acid where tartaric acid is formed, then it is concentrated and precipitated out. So, we get tartaric acid mainly from grape juice. Then it can be synthesized chemically from succinic acid. Succinic acid is subjected to this Hell-Vollard-Zielinski reaction, and with more amount of bromine we get dibromosuccinic acid, and this is hydrolyzed, we get tartaric acid. Glyoxal, glyoxal CHO, this can be converted into tartaric acid by the addition of HCN. First we get glycosynohydrin and then this cyanohydrin is hydrolyzed. This cyano group is hydrolyzed into carboxyl group. We get tartaric acid. Both these compounds, succinic acid as well as glyoxal, can be obtained from acetylene, and acetylene itself can be obtained from calcium carbide by reaction with water, and you know that calcium carbide is obtained by the reaction of lime and coke. So, basically from some natural sources, that is lime and coke, we can enter into this sequence of reaction for synthesizing various organic compounds. This reaction can be shown like this. This acetylene, acetylene on partial reduction, that is a catalytic hydrogenation with Lindlar's catalyst, we get ethylene. Ethylene on addition of bromine gives ethylene bromide, means across this double bond a molecule of bromine is added up, we get 1,2-dibromoethane or ethylene bromide. This ethylene bromide is treated with KCN. These two bromo they get substituted by cyano. So, we get ethylene cyanide, and then this is hydrolyzed. The cyano group is hydrolyzed into carboxyl group and we get succinic acid. So, acetylene is converted into succinic acid through this route. Then acetylene can be converted into glyoxal also by the ozonolysis. When it is treated with ozone and followed by reductive hydrolysis, it becomes CHO here. It can also be obtained from the ethylene. First, this ethylene is partially oxidized by potassium permanganate to give ethylene glycol, which can undergo a mild oxidation to give glyoxal. So, these are the various sequence of reactions which are helpful in conversions also. When one functional group is related to another functional group during conversions, these type of reactions are very helpful in that. Then another method for the preparation of tartaric acid is from glyceraldehyde by a reaction called Kiliani-Fischer synthesis. Kiliani-Fischer synthesis is a very important reaction and is used up in stepping up of the series, that is one carbon is increased by this reaction, and this reaction is used in carbohydrate chemistry mainly. But here glyceraldehyde can be used for the synthesis of tartaric acid using this reaction. First step involves the addition of HCN to this aldehyde and we get cyanohydrin. This is the cyanohydrin from glyceraldehyde. Now, if this cyano group is hydrolyzed, first it is hydrolyzed in alkaline medium using barium hydroxide followed by acidification, we will get this compound. This CN has been converted into COH, but there is primary hydroxyl here, these two are secondary hydroxyls. This can be oxidized under mild conditions using dilute nitric acid and we get tartaric acid. So, this way starting from glyceraldehyde we can increase the chain length by 1 carbon and we obtain tartaric acid. Then we can obtain tartaric acid by the oxidation of fumaric acid or malic acid. As I said before, fumaric acid is the trans isomer, malic acid is a cis isomer. When they are oxidized by KMnO4, by the oxidation of KMnO4, the 2 hydroxyls are added to the 2 carbon which are joined by double bond. And you must have studied in chemistry of alkenes that the 2 hydroxyls they add to this carbon from the same side. So, this is a regio specific reaction, 2 hydroxyl groups adding on this carbon carbon double bond from the same side. So, when we start with fumaric acid we end up with a DL mixture, and when we start with malic acid we get the mesoisomer. I think you must be familiar with these isomers of tartaric acid which have been discussed while discussing the stereochemistry. Then as far as the properties of tartaric acid are concerned, it gives us a series of salts. There are 2 replaceable hydrogen on 2 carboxylic acids. We can get sodium or potassium tartrate, that is salt on one of the carboxyl group, or both of the carboxyl group from the salt, say with potassium we get is a dipotassium tartrate. Then we can have a mixed salt also from this, like sodium potassium tartrate, that one of the carboxyl is present as sodium salt, other carboxyl is as potassium salt. This salt is named as Rochelle salt. It is used in medicines. Then this is another salt is antimonyl group here and then potassium salt here, we call it a potassium antimonyl tartrate, and commonly it is also known as tartar emetic. So, various salts can be obtained from tartaric acid and they are used for different purposes. Amongst the properties, this can be oxidized by Tollens reagent, that is ammonical silver nitrate, and anything that can be oxidized by ammonical silver nitrate will form silver mirror. So, tartaric acid gives silver mirror test. When this tartaric acid is treated with this ammonical silver nitrate, it gets converted into tartonic acid and silver is precipitated in this reaction. It can also be oxidized by another mild oxidizing agent which is known as Fenton's reagent. Fenton's reagent is ferric ions in presence of hydrogen peroxide. The tartaric acid gets oxidized into hydroxy malic acid, that is 2 hydroxyl groups are there and there is a carbon-carbon double bond here. Then it can be reduced with hydridic acid. First step of reduction of tartaric acid will give malic acid and in the second step it will be reduced to succinic acid. It reacts with HBr also and HBr replaces the hydroxyl group of tartaric acid by bromine. So, from tartaric acid it reacts with 2 molecules of HBr, we get dibromosuccinic acid. Then action on heat. It on heating gives different type of products. When it is mildly heated, simply anhydride is formed. We call it as tartaric anhydride. Then on heating at high temperature, it decomposes, that is decarboxylation occurs and then one water molecule is lost and then other hydroxyl along with the double bond undergoes ketone tautomerism and we get pyruvic acid. Then on heating with potassium hydrogen sulfate, which is a dehydrating agent also, the same reaction occurs, but at a slightly lower temperature. We show this reaction like this, that first water molecule is lost, then this is undergoing a ketone tautomerism and then this carbonyl is beta to this carboxyl and carboxyl group having carbonyl group at beta position undergo decarboxylation very easily, we have discussed earlier, and we get pyruvic acid. So, on heating tartaric acid at very high temperature in the range of about 300 degrees Celsius or with potassium hydrogen sulfate at about 210 degrees Celsius, we get the same product, that is pyruvic acid. Then its uses. Tartaric acid is used as acidulant in soft drinks. Then it is used as effervescent producing tablets. You must have seen certain medicinal tablets also like aspirin tablet. When they are poured into water, some effervescence occurs and they easily break down and break into smaller particles. So, that effervescence in those tablets is due to the mixture of tartaric acid and sodium bicarbonate, they are present. Then Rochelle salt, the sodium potassium tartrate, this is used as laxative in Fehling solution for testing aldehyde and ketones and for silvering of mirrors. Then tartar emetic, that is potassium antimineral tartrate, is used as a medicine as an eliminant of poisons, because when it is given to some person it causes vomiting. So, if person has taken or inhaled some poisonous substance, then by vomiting it can be emitted out. And cream of tartar, the potassium acid tartrate, that is one carboxyl as potassium salt, another as COH as such, it is used in baking powder. Tartaric acid is also used as mordant in dyeing. Now, next we take up another hydroxy acid, that is citric acid. Citric acid is found in all citrus fruits, whether it is lemon, orange, sweet lime, etc. All these fruits, they contain citric acid in very large amounts. Molasses is the thick dark liquid which is left after the precipitation of sugar from the sugar cane juice, and it is waste of the sugar industry, but this on fermentation gives citric acid. Citric acid can also be obtained by the fermentation of sucrose or glucose. Chemically, we can obtain it from glycerol. Glycerol is a byproduct of the soap industry. The soaps are obtained by the saponification of oils and fats, and one of the product formed there is glycerol. Glycerol is treated with HCl under control condition, where these primary hydroxyl groups get converted into the chloro derivatives. Then it is oxidized this CHOH group now gets oxidized to carbonyl group and we get 1,3-dichloroacetone. Then this is further treated with HCN. Now HCN add across this carbonyl group and we get corresponding cyanohydrin. So it is 1,3-dichloroacetone cyanohydrin. Then this compound is treated with KCN. Now these Cl groups here, they are also substituted by cyanide and we get a tricyano group, which on hydrolysis gives citric acid, because each cyanide gives one carboxyl group here. So this is one of the very important method for the preparation of citric acid from glycerol. Then citric acid is also obtained by using a Reformatsky reaction. We have earlier discussed this Reformatsky reaction, but I will briefly revise it. This Reformatsky reaction is the reaction of alpha bromoesters with aldehydes are ketones. These bromoesters, in presence of zinc, they form this ZnBr here and then they add on to aldehydes are ketones. We get this type of compounds where is OZnBr and it gets hydrolyzed to ultimately give us this OH, and we get a hydroxyl group at the beta position of the ester. So this is a very important method for preparation of beta hydroxy esters, which can be converted into beta hydroxy acids. So using this reaction between these two compounds, one is ethyl bromoacetate. This is an alpha bromoester. This is the alpha carbon having bromine, and it is treated with oxal acetic ester. This is the carbonyl group here of the oxal acetic ester, where its zinc product adds on to this zinc. So reaction is carried out in presence of zinc, and now what happens? CH2ZnBr, which is formed first, it adds across this carbonyl. So this CH2CO CH2H5 is here, this CO becomes OZnBr, it is here, and there is a COOC2H5 which is here, and this CH2COC2H5 it is here. So it is a triester derivative with OZnBr. This on treatment with acid, this is replaced by OH, and this ester groups gets hydrolyzed to COH and we get citric acid. So Reformatsky reaction is used for the preparation of citric acid. As far as the properties of citric acid are concerned, it can also give a series of salts because it has got 3 carboxyl groups. It can give us a monopotassium citrate, a dipotassium citrate, or a tripotassium citrate. They can be sodium or some other metal also. Then one of the property of the hydroxyl group, it can be easily acetylated. Citric acid on treatment with acetic anhydride gives monoacetyl citric acid. This OH gets acetylated here. Then reduction. HI can reduce citric acid into tricarballylic acid. This OH is replaced by H reduced here and we get an acid called tricarballylic acid. Next reaction is action of sulfuric acid. Citric acid on treatment with fuming sulfuric acid undergoes a reaction in which a molecule of water and a molecule of carbon monoxide is lost and we get acetone dicarboxylic acid here. Then formation of complex salts also takes place using citric acid as a ligand, and one of the very important complex salt that we used is Benedict solution. In Benedict solution, citric acid is complexed with copper ions. The Benedict solution is used for testing carbohydrates. Then action of heat. On heating at a low temperature of about 150 degrees Celsius, citric acid gives aconitic acid. This is simply by the loss of a water molecule, because this hydroxyl group is now alpha hydroxyl with respect to this carboxyl, and beta hydroxyl with respect to these two carboxyl. So, it loses a water molecule taking hydrogen from the neighboring carbon. So, this acid is called aconitic acid, but if we heat citric acid at high temperature, then two sequence of reactions they begin and we get various products in that. On strong heating, one sequence of reaction is that one molecule water and one carbon monoxide is lost, we get acetone dicarboxylic acid. This is the same product that was obtained on treating with fuming sulfuric acid also. Then this loses a molecule of carbon dioxide, that is decarboxylation occurs at one of the carboxyl group and we get acetoacetic acid. This undergoes decarboxylation at this carboxyl group also and we get acetone. So, one sequence that begins from citric acid high temperature ends at acetone. Then another sequence of reaction that begins is by the loss of water from these two carbons, giving this aconitic acid that is obtained by heating citric acid at 150 degrees Celsius also. But since here we are heating at high temperature, then aconitic acid first formed gets converted into either of the two products. One is called etaconic acid. This etaconic acid is obtained by the decarboxylation of this carboxyl group. And if the decarboxylation occurs here, we get another compound which is named as this citraconic acid or mesaconic acid. Actually, here there is a carbon-carbon double bond and each of these doubly bonded carbon contains two different groups, this carboxyl group, a methyl group. This carbon contains a hydrogen group and a carboxyl group. So, this compound shows geometrical isomerism. Both the isomers are formed. The cis isomers is named as citraconic acid. The trans isomer is named as mesaconic acid. So, we will get the mixture of these two acids here. Then on further heating, etaconic acid can lose a water molecule between two carboxylic acids forming etaconic anhydride. And here citraconic acid, the two carboxyls are on the same side, may lose a water molecule to form citraconic anhydride, whereas a mesaconic acid cannot form the anhydride. So, these are some of the important reactions of citric acid, and now let us take uses. It is used as food acidulant and in many soft drinks. It is used in jams, jellies, candies, as mordant in dyeing. Magnesium citrate is used as an antacid. Then its esters are used as plasticizers for lacquers and varnishes. It is also used for cleansing metals, because on the metals mostly the blackening that occurs is due to formation of some salts, and when we rub it with citric acid, that metal complex is formed and it can be washed out. So, this was about the three important hydroxy acids that form the part of our food regularly. Now, let us summarize what we have done today. We discussed that what are hydroxy acids, then we discussed the methods of preparation and properties along with some uses of malic acid, tartaric acid, citric acid. In our next session, now we will take some unsaturated carboxylic acids and we will also discuss the acid derivatives in our future sessions. Thank you.